Okay, the next advanced integration technique we're going to take a look at will involve a topic hopefully you recall from last year, and that is partial fractions. Realistically, if you remember everything about partial fractions and how to carry those kinds of problems out, this particular section should be super easy. But if you need a review of partial fractions, I think that's really going to be the main component of this lesson, because once you apply the partial fraction process to an integral, that resulting integral should actually be fairly easy for you all to integrate. So let's take a look at partial fractions again. Okay, so what is this idea behind a partial fraction? Well, if you recall way back when you were first introduced to fractions, and especially adding or subtracting them, and maybe in this particular case here, the puzzle you had to put together was what is 1/2 plus 3/4. And of course, there was a whole process to figuring that out, but ultimately you found those common denominators and did what you needed to do, and you found that the answer was 5/4. So it wasn't a big deal. So what is this idea behind a partial fraction? Well, in these kinds of problems, what we're trying to do is start with the answer of 5/4 and figure out what two fractions would have been added together to give us that result of 5/4. And the reason we're going to want to do that is because if we can break down something complicated, not that 5/4 is complicated, but if we wanted to break down something more complicated, possibly into two simpler things with regards to taking integrals, then maybe that would be something that would help us ultimately solve an integral that we don't know how to do. So kind of what I just said a moment ago, the question is, why would you want to decompose fractions? And that's just another way of saying finding the partial fractions. Decomposing fractions just means finding the fractions that gave you another fraction. So decomposing a fraction gives you two fractions which can be a little simpler and therefore easier to integrate. And that's kind of the goal with these problems. So I think probably the main hurdle to get over is, how do you know a problem is going to require this process? Well, we'll take a look at that in this first example. So partial fractions are just simpler fractions which sum to give another fraction. So this will be our first intro to this type of a problem. So let's pretend this problem wasn't being presented in this lesson 8.4. And I just said, let's try to use what we know right now up until this lesson to integrate this. The first thing I hope you'd realize is we can't simplify it. There's nothing we can do here. I know we can factor out an x in the bottom, but that really won't help us do anything. The second thing we should consider is a u substitution. The only thing we could call u would be the denominator, but again, if you want to try that, you'll quickly see that won't work. This also doesn't fall into any of like the arc inverse trig function kind of problems, so we can throw that out. So then why is this, and by the way, it's also not a integration by parts since we're not multiplying two functions, so then why is this a candidate for a partial fraction kind of problem? Well, you'll notice if we do factor out that x in the bottom, which would be x times x minus 1, that leads us to believe something. That leads us to believe that there were two fractions that were added or subtracted together that gave us this new fraction. And if maybe we found what those two fractions were, then maybe we could integrate those two things separately because they would be easier than this current form that we have right now. So that's what we're going to do. Let's go ahead and take this fraction and decompose it into its partial fractions. And it's really just a couple steps, even though it's a little involved. It really just is two steps. The first thing we're going to do is rewrite our fraction as the sum of two fractions. We know in the bottom of one of those fractions there was an x. And we know in the bottom of the other fraction there had to have been an x minus 1 because of this denominator we see. The only thing we don't know is what the numerator of what both of those fractions were. So then how do we proceed from here? Well, just like any time we're dealing with fractions, we need to have a common denominator. And you'll notice for the a over x fraction, it's missing the x minus 1 in the bottom to have that common denominator of x times x minus 1. But of course, we can't just put it in the bottom or we've changed the problem, so we also need to put it in the top of the fraction. Same thing goes for the b over x minus 1 fraction. That denominator is missing that x in the bottom, but of course if we put it in the bottom, we also have to put it in the top. So that's kind of where we're at. We just found the common denominator so we could set up these fractions correctly. The next thing we need to do is, since they do have a common denominator, is to combine these two fractions. You'll notice that if we distribute that a to both of those terms, we'll get ax minus a plus bx, all divided by now our common denominator of x times x minus 1. The other thing I'm going to do here is you'll notice we have two x terms that I want to combine together. But since we don't know what a and b are, all we can really write it is a plus b times x. If a had been 2 and b had been 3, of course we would have put 5x, but we don't know what a and b are, so we're just going to have to write that as a plus b all times x, and then we still have minus a in the top. This is an identity in a sense, so everything on the right side of this equation should still be equal to our original problem, which was on the left side. After that, now we're kind of ready to solve this problem. Just kind of realize something here. There's an invisible x term in this numerator, and you'll see why we need to realize that, but it's really 0x minus 1. We of course never really want to write that, but because there's a 0x there, we can do some equating. First, we can realize that these two denominators, because they're in both of these fractions in this proportion, they would of course just cancel out. The next thing we need to realize is that when we have these two things being equal to each other, these two numerators equal to each other, it turns out, if you weren't aware of it, that the x terms are equal to each other and the constant terms are equal to each other. The reason we have a plus b equals 0 is because those are our two x terms. We have a 0x and an a plus b x. So we know that those coefficients in front of the x's are equal to each other. So of course we can just put a plus b equals 0 because those are our x terms. Our constant terms also have to be equal to each other. Remember, this is an equation, so all of this has to be equal, which would mean our constants have to be equal. -1 would be equal to -a. Once you realize that, this problem is very straightforward now. Of course, on the right side here, we can divide by -1, so a is 1. And if we take that a and plug it in over here, then b would be equal to -1. And now we've kind of achieved what the goal was. We needed to find what a and b were, which were the numerators of this partial fraction. So now we can plug those in. We know a is 1, so that'll be 1 over x, and we know b is -1. I'm going to move that negative to the front of the fraction and just write it as -1 over x minus 1. So hopefully that kind of reminds you of what you did back last year in pre-cal, because ultimately that's really all there is to it. After that, it's really just a basic basic calculus problem. We know that this thing that we couldn't integrate from before is equal to this thing, which I'm not sure if you've really thought about it, is integrable. The integral of 1 over x is ln absolute value of x. The integral of 1 over x minus 1 is going to require just a basic u substitution where we call u x minus 1, and then nicely du is equal to dx. So this integral is really du over u, which is another nice and easy integral, a natural log antiderivative. So this new expression, hopefully now that you can see this, is much easier to integrate than that original expression. And again, like we said a second ago, the integral of 1 over x is ln absolute value x minus ln absolute value of x minus 1. Remember, this was really the natural log of the absolute value of u. And then, of course, because these problems are so involved in a lot of steps, please don't forget that plus c at the end, because that's your general solution or your antiderivative. Okay, so that last example we did in the last slide was an example of something called a non-repeating linear factor problem. The reason it's called non-repeating is because both of the factors in the bottom weren't the same, and also both of those factors were linear. This would be another example of a non-repeating linear factor kind of problem, and honestly, those are really the only types you have to worry about for the AP test. There are many other types of these partial fractions we can do, but these are the ones we're going to focus on mainly. So again, we have this integral, and I guess we can go through the process of thinking about why we can't integrate this, but I'll kind of let you think about that. And let's just jump to what really matters here and realize that this is a partial fraction problem. So we need to write our original fraction as two separate fractions, a over 2x plus 1 and b over x minus 2. And our goal is to figure out the a and the b. So again, we need to find a common denominator. We know the common denominator is right here. So what is the a fraction missing? Well, in the bottom, it has an x plus 2x plus 1, so we need that other x minus 2, but of course if we put it in the bottom, we also have to put it in the top. The b fraction has an x minus 2 in the bottom, but it's missing the 2x plus 1. So again, we can put it in the bottom so we have that common denominator, but we also need to put it in the top so that we don't change this problem. Just like you saw in the last problem, we need to add these two fractions together because they have common denominators. And within doing that, just realize we're going to have to take the a and distribute it, and we're going to have to take the b and distribute it, and we'll end up with ax minus 2a plus 2bx plus b. After we get that, we can kind of group the x terms together, and we're really just combining like terms, and we can group the constants together. Remember, a's and b's are constants. Anything with an x would be an x term. So we have our two x terms, which would be a plus 2bx, and we have our two constant terms of b minus 2a, all divided by, again, our common denominator. And like I was saying in that last problem, we don't have to write in the original fraction in every step, but just realize this is an identity. We know these two fractions, or this set of fractions, is equal to the original fraction, I should say. So of course, all of these things are equal to each other. Just like you saw again in the last slide, there is no x term in the top of our left problem, our original problem, so we have to just consider that to be a 0x. Again, we know these denominators will cancel, and if you recall from the last slide, we know the x terms are equal to each other, which would be the a plus 2b is equal to 0, and we know the constant terms are equal to each other, which would be the b minus 2a, and that would be equal to the constant on the left side of 5. After that, we're ready to solve this little system of equations, and there's several ways you can approach it, but what I'm going to do first here is solve this left equation for a, which would mean just subtracting the 2b, which would make it a negative 2b. Now that I know a is negative 2b, I can take that and plug it into my second equation, so that now we just have b's. Instead of negative 2a, I'll have negative 2 times negative 2b. Of course, that'll just become 4b. 4b plus 1b is 5b, and if we divide by 5, we'll find that b is equal to 1. And now we can take that value, plug it into our original equation, or first equation if you want to call it that, and of course, a is going to be equal to negative 2. So again, there's quite a bit of work that goes into these problems even before we can attempt the calculus. So again, if you recall all this partial fraction stuff, you're kind of ready to go with these problems. So now we can rewrite our integral. We know the integral we are really dealing with here is negative 2 over 2x plus 1 plus 1 over x minus 2. Since we have two functions being added and we're taking the integral, we can do each of those separately and just realize both of these are going to be a u substitution. On the left fraction, the u is the bottom, 2x plus 1. On the right fraction, the u is x minus 2. When we do our du, we'll get 2x dx. When we do our other du, we'll get just a dx. And the great news about that is kind of everything simplifies quite nicely. All I'm doing in here in this next step is I'm moving that negative in front of the 2 out to the front of that integral, so you can see that wherever we see a 2dx, we're going to replace that with a du. Wherever we see a dx, we're going to replace that with a du. And of course, we already know the bottom is equal to u, and I'm going to kind of skip over that step. I think at this point in your experience with doing these problems, you might not need to write in this step that I'm skipping, where it would just be du over u plus du over u. If you feel the need to write that in, please do. But ultimately, the final answer, of course, will be the natural log of the absolute value of u for both of these problems. And then when we plug those u's back in, we'll end up with negative ln absolute value of 2x plus 1 plus ln absolute value of x minus 2. And then again, don't forget that plus c. Those absolute values are definitely important because, of course, these values could be negative, and we can't take natural log of negative numbers. So definitely a more involved problem than that last example, but now I want to kind of go over a shortcut method. And actually, before we go over that shortcut method, always keep in mind we should be simplifying our answers completely, if we can. And you'll notice we have a positive ln x, and we have a negative ln x. So I hope you remember that property about natural logs, where if we're adding or subtracting natural logs, that's really a matter of multiplication or division. And since we're subtracting, technically we're subtracting these two natural logs. That would mean we can make this one natural log, where the positive natural log goes in the top, and the negative natural log goes in the bottom. And of course, that'll still need that absolute value around all of that. But to the shortcut I was talking about, there's a shortcut that was developed by an English engineer named Oliver Heaviside. So of course it bears his name, the Heaviside method. And really the advantage to this is you're not going to have to deal with all of this right here. You're basically going to take all of these steps that you see right here and disregard them. The only step we need is this step right here, the very first step in a sentence. So that's where we're going to start. I'm going to start off with that step right here. We're not going to go any further and combine the fractions. We're going to just stop right there, and then of course that's still equal to our original problem back up here. Okay, so what does this Heaviside method tell us to do? Well, the first thing we can absolutely do is just get rid of all those denominators and be left with a nice easy expression here. So how are we supposed to figure out what a and b are just using this? Well, what the Heaviside method says is we need to substitute any convenient values for x so we can get those values of a and b. And what do we mean by convenient? Well, we mean by convenient that it's a value that will end up giving you a 0. Because if you can get rid of either the a or the b, then of course you can solve for whatever one is left over, and it makes it nice and simple. So let's presume I want to let x be 2. If I let x be the value of 2, we'll end up with 5 equals a times 2 minus 2, which is great, plus b times 2 plus 1. The reason we wanted to let x be 2 is that would just cancel and be 0. And of course, we'd end up with 5b, and that is equal to 5, or b is equal to 1. And you can see that matched what we got above. So that worked out quite nicely, and I definitely think a lot quicker. So then what value would we want to pick so that we can find our a value? Well, you'll notice right here, we would need to call x a certain value to make this entire thing 0. What x value would that be? Well, if you think about it, that would have to be a negative half. If we let x be a negative half, then when we do 2 times a negative half, that'll be negative 1 plus 1, which makes all of that go away because it's 0. Here with the a term, we'll have a negative half minus 2, which is negative 5 halves. And when we multiply or divide to the other side, whichever way you want to look at it, we'll end up with a being negative 2, and yet again you'll see that that's the value that we originally got with the long method, if you want to call it that. So I guess bottom line is you can do it either method you want, but certainly because these problems are so involved and you still got to do calculus at some point with these problems, you might want to take the easier path and use this Heaviside method to make your partial fraction piece of these problems a lot easier. Okay, here we have another example of a non-repeating linear factor, but presented a little bit different. You'll notice in the last couple examples, it was pretty easy to see that there were two things being multiplied in the bottom. But in this particular problem, they're not starting us off that way. So what you need to realize is if you can factor the bottom, of course you should always attempt to do that. And now that we have these two factors, we again can see that there were two fractions that were added together that gave us this new fraction. One of those fractions had an x minus 3 in the bottom. One of those fractions had an x plus 1 in the bottom. We just don't know what those numerators were, and that's why we want to find that. And again, just to be thorough here, just realize that this we can't integrate using any other technique. There's no u substitution, there's no way to simplify. We have to rely on this partial fraction decomposition. So I'm going to just kind of throw this up all in one step here so we can kind of see what's going on. Again, remember, the left side of this equation we're setting up is the original problem, or the original fraction. On the right side are the two fractions that gave us this overall fraction here. So what are the two fractions? Well, a had an x minus 3 in the bottom, but it also needs the x plus 1 because that's our common denominator. So we also have to put it in the top. The b fraction has the x plus 1 in the bottom, but it's missing the x minus 3 in the bottom, again, so we can have this common denominator. So we also have to put that in the top of the fraction. And when we do that, of course, we can cancel out all those common denominators, and then we're just left with this expression here. I'm going to go ahead and abandon kind of the long way of doing these problems and just stick with the Heaviside method. We need to figure out what x values we can pick so that we can figure out what the value of a and b are. And if we try to go after a first, if we go after b first, you'll notice if we call x equals -1, we'll get rid of that a term. So wherever we see an x, we're going to plug in -1. 5 times -1 minus 3 equals a times -1 plus 1, which is definitely 0. And then we have b times -1 minus 3. When we simplify all this, we'll get -8 equals -4b, or simply put, b is equal to 2. What value of x will help us find the a value? Well, you'll notice with the b, we have x minus 3, so to wipe that term out, we of course want x to be equal to 3. When we plug in 3 for all of our x values and simplify, we'll end up with 12 equals 4a, and when we divide by 4, we'll of course end up with a equals 3. So I hope you can see in this one example here, definitely the shortcut is not only shorter, of course, but a lot less compact, or a lot more compact, and I think maybe because of that, less likely to give you errors when you're doing all of these problems. Once we do this partial fraction decomposition, we're ready to go now. We can plug in a, we can plug in b, and we can go ahead and find this integral. Again, keep in mind, these are u substitution problems. Now, sometimes maybe the u substitution won't really affect anything. And you'll notice here, it doesn't really affect anything. When you call the bottom x minus 3u, we just get du equals dx. So there's no extra number we have to worry about. Same thing goes for the second fraction. When we call ux plus 1, there's no extra number we're getting because du equals dx. So this is just kind of one easy natural log antiderivative. We're going to end up with 3 natural log absolute value of x minus 3 plus 2 natural log of x plus 1 absolute value, and then again, don't forget that plus c. One last little reminder, we've seen this just a few times in our lessons here and very rarely in problems, but I do want to point out this one little fact. Problems like this that you see right here don't need any sort of partial fraction decomposition or a u substitution. What you have to remember is if you ever run across these fractions that are called improper because the biggest power in the top is either as big or bigger as the biggest power in the bottom, what we need to do is use long division first so that we can get this problem to work out. So just as a quick review, of course you can do this in your TI-89 unless you want the practice of doing this long division by hand, but ultimately we want to rewrite this problem more simplified after using long division. And then after that, we can integrate each of these pieces individually since they're separated by pluses or minuses, and then that makes it a nice, easy problem after that. So don't worry too much about the bottom half of this slide. This just is serving as one last kind of reminder of this type of a problem, but you're not going to really encounter these problems in this lesson because, of course, we're focusing on this new technique called partial fractions. Okay, one more example, an AP exam problem. Only thing different here from any of the ones you've seen before is this now is a definite integral. And I guess on top of that, also realize that the bottom needs to be factored. Again, there is no u substitution we can make work out here in this first step. There is no u substitution we can do here to make this problem work out. In the second step, we definitely can't simplify. So of course we need to consider that this fraction came to be with two prior fractions, one with an x plus 2 in the bottom and one with an x plus 1 in the bottom. And again, we don't know what those numerators are. That's where this partial fraction decomposition is going to play a part. So again, keep in mind, when we set up this partial fraction decomposition, we always need to take the original fraction, which is right there, and set it equal to the two other fractions that gave us that fraction. So when we do that, of course, we need to find that common denominator. The a fraction had an x plus 2 in the bottom. It's missing the x plus 1, so we have to put it in the top and the bottom of that fraction. The b fraction is missing an x plus 2 in the bottom, so again, because of that, we need that common denominator. We need to put it in the bottom and also in the top. Once you accomplish that, we know that all of those common denominators would nicely cancel away, and we're just left with that expression. All the numerators are equal to each other. Again, your goal, if you're going to do the Heaviside method, the shortcut, is to figure out what value of x you can pick to get rid of either the a or the b so you can find the other letter. Here, I'm going to start off by I'm going to try to find b first. I'm going to let x be -1. And if we let x be -1, we need to plug in -1 for all those x's. Of course, this worked out nicely because that a term disappears, and then we're left with 3 equals 1b, or b is equal to 3. The other x value we need to pick so that we can find our a value will be -2. If we let x be equal to -2 and plug it in to all of those spots with an x, you'll notice that the b term goes away. The -2 plus 2 is 0, so that b term goes away, and when we simplify, we'll end up with -2 equals -1a, or a is equal to +2. Once you do all that, that was really the pre-cal kind of problem you would have done last year. Now we're ready to do the calculus problem. We know a is 2, we know b is 3, so we can plug those in. And again, be careful, not always, but sometimes you have to make sure you're considering the bottom of these fractions as u's, because every once in a while, like a problem you saw earlier, you could end up with an extra number over in this u box. Luckily for this problem, that doesn't happen. U is equal to x plus 2, so du is equal to dx. U is equal to x plus 1, so du is equal to dx. So there's no extra numbers we have to introduce into our integral over here to account for those extra numbers. So then what's the result going to be? Well, the result's going to be 2 ln x plus 2 in absolute value, plus 3 ln x plus 1 in absolute value, and be careful here, no plus c. We're evaluating a definite integral, so we'll put that bar notation from 0 to 1. Okay, so I guess the main reason I wanted to do at least one of these definite integral examples with you is maybe the way you should approach the evaluating using the fundamental theorem of calculus. I'm going to notice something here. That 1 and 0, when we plug it into the x, will never give us a negative number. So we really don't need to worry about those absolute values. And then on top of that, to kind of make the calculations look a little nicer and easier, you're going to have to remember this little property of natural logs. If you have a coefficient on the outside of a natural log, you can move that to the inside of the natural log as a power. So I think that's a little bit nicer to look at. We have ln x plus 2 squared plus ln x plus 1 cubed. And now I think we can apply that fundamental theorem of calculus. When we plug in the top bound of 1, we'll end up with 1 plus 2, or 3 squared, which is 9. When we plug in the top bound of 1 again, we'll end up with 1 plus 1, which is 2 to the third power, or 8. So this first part you see right here is the result of plugging in our top bound. Now we have to plug in the bottom bound and subtract those two values. When we plug in the bottom bound, we'll end up with 2 squared, or 4. And in the second piece, we'll end up with 1 cubed, or 1. Okay, so I didn't print the answer choices. This is a multiple choice question. I kind of ran out of space here to print the answer choices, but just realize that we need to take this and simplify it as complete as possible. And what you need to recall is that any positive, and by the way, we can distribute this negative here to both of these natural logs. Any positive natural logs go to a top of a fraction. Any negative natural logs go to the bottom of a fraction. So since ln of 9 and ln of 8 are both positive ln's, the 9 and the 8 go to the top of the fraction. Since the 4 and the 1 have that negative attached to it, those two numbers will go to the bottom of the fraction, and then there's only one natural log. We're condensing this natural log, or all 4 of these natural logs, into 1. So it's just ln of the fraction 9 times 8 over 4 times 1, and of course with some simple arithmetic here, you can see that the final simplified answer will be the natural log of 18. Okay, we're going to take a look at one last example here, and it's an example I said probably would not be encountered on an AP test kind of question, but it's definitely worth our time to address another kind of basic problem, but it's going to be a little more difficult, and that is when we have repeated linear factors. The ones you saw before, none of those things being multiplied in the bottom of the fraction were repeated, but here they are repeated, and you'll notice it's being repeated because we have an x minus 1 being squared in the bottom, and there's 2 of those because it's being squared. So for a linear term raised to a second power, we're going to use 2 fractions, one with the linear term and one with the linear term squared. If you happen to recall that back from your pre-cal days doing these partial fractions. So the way this problem is going to look is we're going to have an a over 1 of the x minus 1's, and then we're going to have a b over not another x minus 1, but an x minus 1 squared. The last term we're going to have is c over that last factor in the bottom of x plus 1. So hopefully that's giving you some reminders of what you saw last year. But after that, it's still really the same process you saw with the previous examples. We just have one extra fraction we're dealing with. So let's go through this a little slow here. The a fraction already has an x minus 1 in the bottom, so it's missing another x minus 1 in the bottom and the x plus 1. So of course we want that common denominator, but we also have to put those new things in the top of that fraction. For the b fraction, all it's missing is the x plus 1 of the common denominator, so of course we have to also put that in the top of the fraction. For the c fraction, it's missing the x minus 1 squared, so it can have that common denominator. So then again, if we put it in the bottom, we also have to put it in the top of that fraction. So you can see, definitely looks a lot messier, but with this Heaviside method, remember, luckily all of this goes away. I'm kind of skipping a step here, and I'm not rewriting that fraction right here, but remember, it's still equal to all of these three fractions, so all of those denominators we can cancel away. And ultimately, we're left with this big expression here, with the a, the b, and the c. So if we apply this Heaviside method, we just need to figure out some x values so everything kind of works out nicely. And I'm going to notice the first x value that makes things work out nicely is x equals 1. The great thing about choosing x to be 1 is you'll notice in the a term we'll get a 0 times 2, which basically means it goes away. In the c term we'll end up with a 0, so that c term goes away. So b is pretty easy to find in this particular case. We have 2b equals 4, or b is equal to 2. So what would be another good candidate for choosing a convenient x? Well, you'll notice -1 also works out nicely. If you choose -1 to be the value for x, you'll notice in the a term we'll end up with another 0. We'll have -2 times 0, which of course makes that go away. When we let when we let x equal -1, the b term also goes away. And then we're just left with that c term, which would be 4c, and when we divide by 4, we're left with c is equal to -1. So you can see how this Heaviside method really can simplify things that would ultimately be fairly more complicated. But the last x value is kind of the trickier one here. If you notice, there is no x value that we can pick that will easily give us the value of a. There really is no x value that we have to do that. When you run into that situation, especially since we already know since we already know b and c, the best value to pick after that is just 0. It's the easiest number to plug in, and you'll notice if we let x be 0, we'll end up with 0 on the left side, 4 times 0. We'll end up with this negative a term. We'll end up with b, and then we'll end up with a plus c. So technically, we'd kind of be stuck here if we hadn't done or what we already done. We know b is 2, so we can take that and plug it in. We know c is -1, so we can take that and plug it in. And just like that, a is very easy to find. Once you plug in the b and the c, which we already found, it turns out a is equal to 1. So you would have pretty much stopped right there back in your pre-cal days and kind of left that as your answer right here. But don't forget, we were doing a calculus problem here where we were trying to integrate that problem at the top. That was an impossible integral to do unless we took it and decomposed it into its partial fractions. Now that we did, we can take the integral of each of these terms separately and just realize that x minus 1 will be a u, and then also the x plus 1 will be a u. But be careful here. Don't kind of get caught up in always thinking that you're going to get a natural log. In this first green term, it's going to be a natural log because it'll be du over u. In this last term, we'll get a natural log because, again, it'll be a du over u. But be careful with this middle term. In this middle term, we'll actually end up with 2u to the -2 power. And that's important because, of course, that doesn't need that natural log antiderivative. Once you realize that, then the answer should be straightforward. We'll have ln, absolute value of x minus 1. When you integrate 2u to the -2, you'll get -2 over x minus 1 minus the natural log of the absolute value of x plus 1. And then again, because it's always worth mentioning because of how long and complicated these problems are, please don't forget about that plus c at the very end.